Hello everyone. Today I'm going to talk about a recent paper called Simple and Effective Unsupervised Speech Synthesis by Alexander H. Liu, Jeff Lai, Wei-Ning Hsu, Michael Auli, Alexei Baevski, and Jim Glass. What is speech synthesis? Speech synthesis is also sometimes called as TTS or text to speech, but speech synthesis is a general name which people use when you want to generate audio or speech using a conditional or unconditional model. But in case of TTS, we feed text as input and generate audio. In the other way, you can think of it as conditioning or conditional generation of audio based on given text. And the conditioning is done using text or phonemes of that text. So in this tutorial, we will see how this can be done, or this text-to-speech can be done, or built. Text-to-speech models can be built using an unsupervised manner. That's why the name unsupervised speech synthesis. And in this tutorial, we'll first see the overview of the paper, of this paper, and then we'll see what the unsupervised TTS is, or how they are achieving this unsupervised text-to-speech, and at the end we'll see the experimental setups and results. So as the name itself says, the paper is a very simple and an effective way to do unsupervised text-to-speech, and the paper basically puts together the blocks or the pieces which are built for speech recognition or unsupervised speech recognition and text-to-speech algorithms which people have built over the past 10 years, which are basically the deep learning models. And I mean, the TTS has been there for a very long time, but we are talking here about the deep learning based models. And the model uses only unlabeled audio and unlabeled text. What does it mean? In the current setting, or in the current way of doing TTS, what people do is they first take some text and they say, or they give it to an actor or a professional to read it out. So that way you have a pair of text and audio, and there could be, you need let's say 20 or 30 hours of audio in order to get sorry about that, in order to get a good text to speech model, right? So this is time consuming and expensive, because we don't want to give text to a professional actor, and we don't want them to just record and give it back to us so that we can train our TTS model. Can we do this in an unsupervised way? Because we can find a lot of text data and we can find just a lot of audio data on the web. Can we just leverage this audio and text data separately and then do build a TTS engine, right? So that's what this paper does. So we will see how that is done in the coming slides. The algorithm or the proposed approach of this paper in the coming slides. But that's the main idea. And the experiments of this paper shows that this unsupervised TTS model can synthesize speech which are close or similar to the supervised counterpart of it, which is great, because now, I mean, if it is similar to supervised model, why do we need a supervised TTS? We can simply get away with the unsupervised speech TTS model, and we don't have to we don't have to spend a lot of time and money in collecting the data set, right? And the paper says, like I said, the paper shows a good good comparison between the supervised counterpart, and the naturalness and intelligibility of the audios are really good. I'll show you or I'll play the audio files which are generated using these unsupervised TTS models at the end, and you can listen to them later. Also, I'll give you the link, and you can see it yourself. So let's understand this unsupervised TTS algorithm step by step. First, we'll look at the proposed approach of the paper. Basically, we will see the overview of the full architecture. We'll see what's going on. and I'll explain the blocks inside that big picture, and then we'll see the wave-to-wake uh, unsupervised 2.0. So basically, it's a wave-to-wake. U means unsupervised, and there is a 2.0 version of wave-to-wake unsupervised model. So if you're closely following the papers which are released from Facebook research team on the super speech recognition ideas, so you would have seen unsupervised speech recognition model which was released last year, and I also have a tutorial of that paper in my YouTube channel. You can check it out later. And recently, I think around 1 month ago, they released this wave-to-wake unsupervised 2.0. I will show you the comparison of the wave-to-wake unsupervised, the 2021 paper and the recent one, and they are using this wave-to-wake unsupervised 2.0 in this paper, and I'll show you what changes they made with the 2021 model, and so on. And we will see how the pseudo labeling of speech is done using unsupervised ASR model, which is basically this wave-to-wake 2.0 unsupervised 2.0 model. And we'll see how the unsupervised TTS is trained using the pseudo labels generated using this unsupervised ASR model. Okay, so this is an important slide because this is what is happening in this algorithm. So this is the main diagram. So this blocks explain, or this slide explains the entire paper, or just the proposed approach of this paper. So what all is there? You can see there is 3 stages, right? There is stage 1, there is stage 2, and there is stage 3. So in stage 1, they are training an unsupervised speech recognition model, so unsupervised DSR, with wave-to-wake unsupervised 2.0, right? You may ask why. We'll see why, right? So how is it done? So you have some unpaired text, which is basically some random text, which is in the same domain as this random audio or unpaired audio, but not exactly the same text in this. Like for example, you should not use LibriSpeech text here. LibriSpeech text with LibriSpeech audio is here, right? That is not a right way because you have the same occurrences or same audio or same text for this audio here. So the model will simply kind of not really overfit. I would say it's basically you are kind of giving supervision to the model. But if you really want an unsupervised or really want a good unsupervised model, then you have to make sure the sentences which are in this unpaired text data set is not in this audio data. Right. So once you have that data, you can use a lexicon, which is basically some sort of a G2P model, right? You can use a dictionary, right, like a CMU dict, or you can use some sort of pre-trained G2P model, which is trained like a sequence approach, right? So in this paper, they are using pre-trained G2P, which is basically sequence neural network model, which takes in sequence of characters and generates sequence of phonemes, right? That's why it's called G2P. So when you have once you have the output from lexicon, which is basically a sequence of phonemes for a given text, and you take some random audio and give it to the recognizer, and the recognizer also generates some sequence of symbols, which we can't really say they are phonemes because we don't know what they are. They're just sequence of symbols. And the idea of this unsupervised wave-to-wake model is to train a discriminator and also train the generator such a way that the model or the discriminator is not able to distinguish between the original or real phoneme sequences and the generated phoneme symbols, right? So that's the idea. So that way we are training this generator, which is basically a speech recognition model, to generate phoneme-like symbols or phoneme-like symbols, right? So this is how the unsupervised speech recognition model is trained. So if you want to understand in detail, in depth, how unsupervised wave-to-wave models are trained, I think you should go and read the unsupervised speech recognition paper from Facebook, or you can just listen to my one of my tutorial on this exact same paper. We have to make unsupervised paper, and how I um, in that tutorial I explain in detail how this unsupervised ASR training is done. So let's say you trained the model or trained the recognizer and discriminator, and let's say the losses converge, and now you have a good unsupervised ASR model with you, right? Now what to do? Now what we are going to do is we are going to go to the second step. In the second step, we are going to train a text-to-speech model. You can ask how are you going to train text-to-speech model when you don't even have text as input and its corresponding audio, right? So this is how it is done. Let's say you have some unpaired audio data, right? So let's take an example of LJ speech, but in LJ speech, just ignore the transcripts, right? So you take LJ speech data, which is the text-to-speech data, and you are only, I am saying you are only considering the audio, you are ignoring the text, right? And you take the audios and feed it to this recognizer, which you just trained. This, I mean, the coloring here, you can just look at this here. So this color means it's fixed, means it's not trainable. This color means it is trainable, and this blue box means it's required, which you can take it from any open source GTP model, right? So now, like I said, you take the audios and feed it to recognizer, and as you know from the previous step, this recognizer will generate some sequence, some symbols for any given audio, right? Which are called pseudo labels in this case. Now you have a pseudo labels for this audio, and you can also get MEL spectrogram for the same audio, right? So MEL spectrogram is basically generated using audios, right? We don't need text or anything. So now you have a mapping of, or you have pairs where you have pseudo labels P and you have spectrogram S, and you can index them as I because you have I going from 1 to N, and N could be 10,000 or 13,000 files in our case, right? And you have this data set, paired data set now. Now the idea is to train a text-to-speech model. We can't really say it's a text-to-speech model. You can simply say it's some sort of symbol-to-speech model where it takes some sequence of pseudo labels, which could be phonemes because they look like phonemes because that's what we made the model train, right? Sequence of phonemes, and then it takes takes them as input, and it's a sequence model which is basically encoder decoder. So the encoder takes pseudo labels and the decoder generates sequence of spectrogram or sequence of spectral vectors, which are basically which is basically the spectrogram matrix, right? Now there's one more part here which is kind of ignored. It's not really ignored. I think that will come in the third step. So now once you have this training, so you can say like how the model is trained. The model is trained using L1 loss, which is basically comparing the generated MEL spectrogram with the ground truth MEL spectrogram, and you just propagate to the text-to-speech model and train the text-to-speech model until convergence, right? So now you have two things. One is you have unsupervised speech recognition model, and then you have an unsupervised text-to-speech model, right? Now you can say, okay, this is all good, but in case of real text to speech, what do we do is we give a text and we ask the model to generate audio for it, right? We don't want spectrogram or a MEL spectrogram or anything. We want to feed in text as input and generate audio, right, for that text, right? How do you do that? That's the third step, which you can think of it as synthesis step or inference step, right? Where you take a target text, which can be anything. Let's say she had your dark sodium greasy wash water earlier, something like that. And then you feed it to lexicon, which is already available. And then you get a sequence of phonemes, right? And now, which is basically, I mean, those sequence of phonemes are called pseudo labels. And they are not really pseudo labels here because you are actually giving the phonemes as input, not really pseudo labels. But we will see what happened or how the model is able to do this text to speech even for phonemes, right? So let's say you give phonemes as input because they are all in the same range, because pseudo labels are, let's say, 39 pseudo labels, and in case of phonemes also you have 39, right? And you feed it text to speech, and text to speech gives you the Bell spectrogram, and then you have to generate audio. We don't want spectrogram, right? So for that you use something called vocoder. There are many vocoders available these days, and you can choose a vocoder of your liking and then generate the audio, right? Simple. Now comes the question. We didn't even train the text to speech model using the true text, which is true phonemes, and how the model was able to generate audio. So what happened in this case of in the first step is we forced the discriminator, or we forced the recognition model to generate sequences which are similar to the real phoneme sequences, right? In this case, right? Because we used a discriminator and we propagated discriminator laws to this recognizer, and we force this recognizer model to generate phoneme sequence like sequences, and we use those sequences to train the text to speech model. And if you look at it, whatever the pseudo labels are, the pseudo labels are actually similar to phonemes. So that's why during inference stage, you can actually feed phonemes instead of pseudo labels, because they are kind of same. They are similar because we made made sure the ASR model, or the the recognizer, generates those kind of pseudo labels, right, for any given audio. So that is why the model, now we can use this text to speech model trained with pseudo labels to generate synthesis, to generate audio for any given text, and it takes phonemes, real phonemes, as input, right? So this is the overall idea of the paper. Hope you guys understood. Now let's just talk a little bit about what is this Wave-to-Wake 2.0 unsupervised. So basically, if you look at this picture, this is basically Wave-to-Wake 2.0, Wave-to-Wake view. As you can see here, Wave-to-Wake 2.0, not really this, so let's call this as Wave-to-Wake U, which is basically Wave-to-Wake unsupervised. This is the version 2 of it, the same thing, but version 2. What changed is the pre-processing steps. In case of Wave-to-Wake version 1, let's call it as V1 simply. In the V1 step, they had this pre-processing step where they do the k-means clustering and PCA reduction, and then cluster pooling and adjacent pooling and everything to get this sequence of symbols, right? Because when you get the feature vector from Wave-to-Wake, what they will have frame, the output will be per frame, right? And you may have thousands of frame, 1000 frame per second. You don't want 1000 frames per second, because we want to feed it to a discriminator which takes input which kind of has a less number of symbols, which are similar to the amount of phonemes in that audio, right? Unique phonemes, not unique, like the phonemes, the actual phonemes of that audio. So that's why we do all this pre-processing. But what they did recently is, in the Wave-to-Wake, in the V2 version, they just replaced this whole pre-processing with this simple batch norm layer, and they also use something called auxiliary self-supervised objective, and that kind of changed this, removed all these pre-processing things, and it became quite simple, right? So that's the difference between a simple comparison between the Wave-to-Wake unsupervised with version 1 with version 2. Now, as I said, like I told about this already. So it's just pseudo labeling using unsupervised ASR model. Just generate, after you train the Wave-to-Wake model, generate pseudo labels for that given data set. It could be Libre TTS or LG speech. And then, like I said, you train the sequence TTS model. In this case, it's a transformer TTS model. The transformer TTS is one of the TTS paper, which is, I think, published back in 2020 or 2019, and it takes pseudo labels as input during training and takes phonemes as input during inferencing or synthesizing, right? and for any given input, it generates mil spectrogram, and you can feed the mil spectrogram to the vocoder, which would then generate the audio. Now let's look at the experiments. So basically, you have two data sets. One is the audio data set. You just have the audio, and you have just the text, right? Audio and text, they are like unpaired. Like I said, they are not really from the same data set, right? So for audio case, you have two data sets. One is LJ speech, which is a single speaker, female single speaker data set, which has 24 hours of audio and 13,000 utterances. In Libri speech, you have, it's a multi-speaker data set, which has like 500 hours of audio data. And this is actually derived from Libri speech data set, or Libri speech ASR data set, and it has roughly 2,500 speakers. And this is done. I mean, random selection of 6 speaker is done to just make sure it's in comparison with some of the one of the old paper, right? And for text, you have they use the Libri speech text itself, but you have to make sure you remove all the utterances, or the text of all the utterances which are in this LG speech or Libri TTS. So that is one of the important step, right? And for lexicon, they use this the G2P, which is available in this Git repo, open source model. And for experiment, like I said, they train the transformer TDS. Like if you want in detail, like how this transformer TDS, like what is a pre-net and post-net architecture and everything, you can check the paper. And speaker embeddings for this multi-speaker TDS is taken from the speech brain toolkit. There is a model trained with some eKappa data set, I think. They use that those speaker embeddings. And for vocoder, they use parallel waveGAN for single speaker and IFI-GAN for multi-speaker. Let's look at the results. So some of the, you have to understand some of the evaluation metrics they are showing here. MOS is basically mean opinion score. So it's basically rating for given by multiple people for a given audio, right? And that is MOS score, and word error rate is simply word error rate is basically the ASR metric, and they are using the Google ASR on the synthesized audio, and they are comparing or calculating with the ground truth transcripts. So if you look at it, you have natural, which is basically just the audio, true audio, which is recorded by humans, and mean opinion score is 4.05. I mean, it's okay, because I think it depends, because sometimes you will see numbers like 4.5 in some other paper. It all depends on the subjects you are using to give the scores. So you just have to make you just have to think this natural is basically your upper bound. And then you have supervised, which is basically supervised TTS trained using the transformer TTS model, using a standard text as input and spectrogram as output approach. And it's quite close to the MOS, quite close to the natural audio or natural sound, right? And unsupervised comes here. It had some phoneme error rates, or phoneme errors, but the intelligibility is close to the supervised model, right? And that is one metric, which is mean opinion score metrics. Second is word error rate. Like I said, you take the synthesized audio, feed it to Google ASR, Google ASR API, and then you get the transcript and compare it with the ground truth transcript and measure the word error rate for it, right? And for natural, you have 18% word error rate, which is bad. I mean, I don't know what type of Google API they're using, but 18% is bad because these audios are like quite high quality. But anyway, you can think of it as a upper bound, right? And you have supervised. Remember that word error rate should be lower, which means lower the better. So for natural, you have lower, and supervised is generating good quality audio, and that's why you have good word error rate. Not good, 19% is not good, but compared to the natural. And unsupervised, if you So in case of unsupervised, if you feed the ASR text, you get 21% order rate, and if you use ASR transcription, um, you get 22%. Nothing much difference. Now there is another kind of testing they're using, something called A/B testing. So which is basically what they do is it's very simple. Even we used to do back in 2015-16 time when we were building TTS engines. So the idea is very simple. So you take an audio or two audios and play to a subject and ask them which one is good, right? And whichever they say it's good, which means that one gets the point. So if you're getting 50%, means there is not much difference between the supervised generated audio or unsupervised generated audio. So basically, this A/B testing is done for the supervised model and unsupervised model, right? So so if 50% for naturalness, the preference is 50% means people are, I mean, it's kind of a random, right? So people are not really finding any difference between the supervised output and unsupervised output, which is really good, right? Which means we are like close to the supervised model. But in case of intelligibility, somehow the people were preferring supervised model compared to the unsupervised, right? So that is one of the other metric. And finally, for Liberty TTS, you have same metrics measured. Like for example, in case of MOS, you have 4%, 4 for natural and 3.81 for unsupervised, and 3.7 for sorry 3.881 for supervised and 3.71 for unsupervised. And like you all know that in case of multi-speaker TTS, the naturalness or the quality is little lower compared to the single speaker counterpart of it. So it is good. I mean, it's okay. It's not that bad because it's close to. I mean, it's just 0.1% off, 0.1 point off compared to the single speaker model, right? And in case of order rate, again, the unsupervised model is suffering compared to supervised and natural. And before we close before we stop the tutorial, I want to give a link or a link to a paper called Unsupervised Text-to-Speech Synthesis by Unsupervised Automatic Speech Recognition. This is a older paper compared to this paper, and in this paper also, I mean, this paper is also similar to the current paper, and basically it does almost the same thing, right? So they have G2P here, as you can see, they have discriminator here, so good, and they have wave to vec, which is basically the old one, and they have some kind of generator which generates phonemes, right, from a given audio, and they use the discriminator to differentiate between the pseudo labels and the real labels or real phonemes. And then once you do that, they train the tachotron TTS model, right? They, in this case, they are training tachotron in this paper, but in the paper, so when I say in this paper, it's this paper. The other paper, I mean the paper which I just explained in the last slide. So the only difference is they have tachotron 2 here, and there they have transformer TTS. And in inference, they are using IFIGAN and Griffin Codon. So this is a kind of a similar idea. I think both the papers are kind of similar. That's the one thing I wanted to let you guys know. And that's all for this tutorial. Thank you so much for watching till the end. And if you like this tutorial, give a thumbs up. And if you want to listen to, or if you want to see this kind of tutorials in the future, please subscribe to my channel. Thank you.